In this lesson and in this series of lessons, we will introduce you to the concept of data structures. Data structure is the most fundamental and building block concept in computer science, and good knowledge of data structures is a must to design and develop efficient software systems. Okay, so let's get started. We deal with data all the time, and how we store, organize, and group our data together matters. Let's pick up some examples from our day to day life where organizing data in a particular structure helps us. We are able to search a word quickly and efficiently in a language dictionary because the words in the dictionary are sorted. What if the words in the dictionary were not sorted? It would be impractical and impossible to search for a word among millions of words. So, dictionary is organized as a sorted list of words. Let's pick up another example. If we have something like a city map, the data like position of a landmark and road network connections, all this data is organized in the form of geometries. We show the map data in the form of these geometries on a two-dimensional plane. So map data needs to be structured like this so that we have scales and directions and we are effectively able to search for a landmark and get route from one place to another. And I'll pick one more example. For something like daily cash in and cash out statement of a business, what we also call a cash book in accounts, it makes most sense to organize and store the data in the form of a tabular schema. It is very easy to aggregate data and extract information if the data is organized in these columns, in these tables. So different kind of structures are needed to organize different kind of data. Now computers work with all kind of data. Computers work with text, images, videos, relational data, geospatial data, and pretty much any kind of data that we have on this planet. How we store, organize, and group data in computers matters because computers deal with really large data, and even with the computational power of machines, if we do not use the right kind of structures, the right kind of logical structures, then our software systems will not be efficient. A formal definition of a data structure would be that a data structure is a way to store and organize data in a computer so that the data can be used efficiently. When we study data structures as ways to store and organize data, we study them in two ways. So I'll say that we talk about data structures as one, we talk about them as mathematical and logical models. When we talk about them as mathematical and logical models, we just look at an abstract view of them. We just look at from a high level what all features and what all operations define that particular data structure. Example of abstract view from real world can be something like the abstract view of a device named television can be that it is an electrical device that can be turned on and off. It can receive signals for satellite programs and play the audio video of the program. And as long as I have a device like this, I do not bother how circuits are embedded to create this device or which company makes this device. So this is an abstract view. So when we study data structures as mathematical or logical models, we just define their abstract view, or in other words, we have a term for this. We define them as abstract data types. An example of abstract data type can be, I want to define something called a list that should be able to store a group of elements of a particular data type, and we should be able to read the elements by their position in the list, and we should be also able to modify element at a particular position in the list. I would say store a given number of elements of any data type. So we are just defining a model. Now we can implement this in a programming language in a number of ways. So this is a definition of an abstract data type. We also call abstract data type as ADT. And if you see, all the high level languages already have a concrete implementation of such an ADT in the form of arrays. So arrays give us all these functionalities. So arrays are data types which are concrete implementation. So the second way of talking about data structures is talking about their implementation. So implementations would be some concrete types and not an abstract data type. We can implement the same ADT in multiple ways in the same language. For example, in C or C++, we can implement this list ADT as a data structure named linked list. And if you have not heard about it, we will be talking about them a lot. We will be talking about linked list a lot in the coming lessons. Okay, so let's define an abstract data type formally, because this is one term that we will encounter quite often. Abstract data types are entities that are definitions of data and operation but do not have implementations. So they do not have any implementation details. We will be talking about a lot of data structures in this course. We will be talking about them as abstract data types, and we will also be looking at how to implement them. Some of the data structures that we will talk about are arrays, linked list, stack, queue, tree, graph, and the list goes on. There are many more to study. So when we will study these data structures, we will study their logical view. We'll study what operations are available to us with these data structures. We'll study the cost of these operations, mostly in terms of time. And then definitely we will study the implementation in a programming language. So we will be studying all these data structures in the coming lessons. And this is all for this introductory lesson. Thanks for watching. In our previous lesson, we introduced you to the concept of data structures, and we saw how we can talk about data structures in two ways. One as a mathematical and logical model that we also term as an abstract data type, or ADT, and then we also study data structures as concrete implementations. In this lesson, we will study one simple data structure. We will first define an abstract view of it. We will first define it as an abstract data type, and then we will see the possible implementations. And this data structure is list. List is a common real world entity. List is nothing but a collection of objects of the same type. We can have a list of words, we can have a list of names, or we can have a list of numbers. So let us first define list as an abstract data type. So when we define abstract data type, we just define the data that we'll store, and we define the operations available with the type, and we do not go into the implementation details. Let us first define a very basic list. I want a list that can store a given number of elements of a given data type. This would be a static list. The number of elements in the list will not change, and we will know the number of elements before creating the list. We should be able to write or modify element at any position in the list, and of course we should be able to read element at a particular position in the list. So if I ask you for an implementation of such a list, and you have taken a basic course in programming, a basic introductory course, then you'll be like, hey, I know this. An array gives us all these features. All these operations are available with an array. We can create an array of any data type. So let's say if we want to create a list of integers, then we declare the array type as integer, and then we can give the size as a parameter in declaration. I can write or modify element at a particular position. The elements are A0, A1, and are accessed something like this. We all know about arrays. And then we can also read elements at particular position. The element at ith position is accessed as AI. So array is a data structure that gives us implementation for this list. Now I want a list that should have many more features. I want it to handle more scenarios for me. So I'll redefine this list here. I do not want a static list, a static collection with a fixed size. I want a dynamic list that should grow as per my need. So the features of my list are that I'll call my list empty if there are no elements in the list. I'll say the size of the list is 0 when it is empty, and then I can insert an element into the list, and I can insert an element at any position in the list and in an existing list. I can remove element from the list. I can count the number of elements in the list, and I should be able to read or write, or rather read or modify element at a particular position in the list. And I should also be able to specify the data type for the list. So I should be able to, while creating the list, I should be able to say whether this is a list of integers or whether this is a list of string or float or whatever. Now I want a data structure which is implementation of this dynamic list. So how do I get it? Well, actually we can implement such a dynamic list using arrays. It's just that we will have to write some more operations on top of arrays to provide for all these functionalities. So let us see how we can implement this particular list using arrays. Let's, for the sake of simplicity of design, assume that the data type for the list is integer. So we are creating a dynamic list of integers. What we can do is, to implement such a list, we can declare a really large array. We will define some max size and declare an array of this max size. Now as we know, the elements in the array are indexed as A0, A1, A2, and we go on like this. So what I'll do is I'll define a variable that will mark the end of the list in this array. So if the list is empty, we can initialize this variable or we can set this variable as -1, because the lowest index possible is 0. So if end is -1, the list is empty. At any time, a part of the array will store the list. Okay, so let's say initially when the list is empty, this pointer end is pointing to index -1, which is not valid, which does not exist. And now I insert an integer into this array. And let's say if we do not give the position at which the number is to be inserted, the number is always inserted towards the tail of the list, towards the end of the list. So the list will be like, we will have an element at position 0, and now end is index 0. So at any time, end marks this variable end marks the end of the list in this array. Now if I want to insert something in the list at a particular position, let's say I want to insert number 5 at index 2, then to accommodate 5 here at this particular position, we will have to shift all the elements 1 unit towards the right. All the elements starting index 2. We need to shift all the elements starting index 2 towards the right. Okay, I just inserted some elements into the list. Let me also write the function call for these. Let's say we went in this order. We inserted 2, then we inserted 4, and then we inserted. In the end, we are inserting 5, and we will also give the position at which we want to insert. So this insert with 2 arguments would be the call to insert element at a particular position. So after all these operations, after all these insertions, this is what the list will look like. This arrow here marks the end of the list in the array. Now if I want to remove an element from a particular position, let's say I make a call to something, to the remove function. I want to remove the element 2, so I'll pass the index 0 here. I want to remove the element at index 0. So to do so, all these elements after index 0 will be shifted 1 unit towards the left or towards the lower indices, and 2 will go away. Now this end variable here is being adjusted after each insertion that we are making. So after this insertion, end will be 0, after this 1, 2, 3, and so on. After this remove, end will be 4 again. Okay, looks like we pretty much have an implementation of this list in the left that is described as an abstract data type. We have a logic of calling the list empty when we have this variable end is equal to -1. We can insert element at a particular position in the list. We can remove element. It's just that we have to perform some shifts in the array. We can count the number of elements in the list. It will be equal to end plus 1, the value in the variable end plus 1. We can read or modify element at a position. Well, this is an array, so we can definitely read or modify element at a particular position. If we wanted to choose the data type, it was just choosing the array of that particular data type. This looks like a cool implementation, except that we have one problem. We said that the array will be of some large size, some max size. But what is a good max size? We can always exhaust the array. The list can always grow to exhaust the array. There is no good max size. So we need to have a strategy for the scenario when the list will fill up the whole array. So what do we do in that case? We need to keep that into our design. We cannot extend the same array. It is not possible to do so. So we will have to create a new array, a larger array. So when the array is full, we will create a new larger array and copy all the elements from the previous array into the new array. and then we can free the memory for the previous array. Now the question is, by how much should we increase the size of the new array? This whole operation of creating a new array and copying all the elements from the previous array into the new array is costly in terms of time, and definitely a good design would be to avoid such big cost. So the strategy that we choose is that each time the array is full, we create a new larger array of double the size of the previous array. And why this is the best strategy is something that we will not discuss in this lesson. So we will create a larger array of double size and copy elements from previous array into this new array. This looks like a cool implementation. The study of data structures is not just about studying the operations and the implementation of these operations. It's also about analyzing the cost of these operations. So let us see what are the costs in terms of time for all these operations that we have in the dynamic list. The access to any element in this dynamic list, if we want to access it using index for read or write, then this will take constant time because we have an array here. And in array, elements are arranged in one contiguous block of memory. Using the starting address or the base address of the block of memory and the index or the position of the element, we can calculate the address of that particular element and access it in constant time. Big O notation that is used to describe the time complexity of operations. For constant time, it is written as, in terms of big O, the time complexity is written as big O of 1. If we wanted to insert element at the end of the array, end of the list, then that again will be constant time. But if we would insert element at a particular position in the list, then we will have to shift elements towards higher indices. In the worst case, we will have to shift all the elements to the right when we will be inserting at the first position. So the time taken for insertion will be proportional to the length of the list. Let's say the length of the list is n, or in other words, we will say that insertion will be big O of n in terms of time complexity. If you do not know about big O notation, do not bother. Just understand that inserting an element at a particular position will be a linear function in terms of the size of the list. Removing an element will again be big O of n. Time taken will be proportional to the current size of the list. N is the size of the list here. Okay, now inserting an element at the end, we just said that it will happen in constant time. It is not so. If the array is full, then we will create a new array. Let's call inserting element at the end as adding an element. Adding an element will take constant time if the list is not full, but it will take time proportional to the size of the list, size of the array if the array is full. So adding in the worst case will be big O of n again. As we said, when the list is full, we create a new copy, double the size of the previous array, and then we copy the previous array, the elements from previous array into the new array. So prima facie, what looks like the good thing with this kind of implementation? Well, the good thing is that we can access elements at any index in constant time, which is the property of the array. But if we have to insert some element in between, and if we have to remove element from the list, then it is costly. If the list grows and shrinks a lot, then we will also have to create a new array and have all this thing of copying elements from previous array into new array again and again. And one more problem is that a lot of time, a lot of the array would be unused. The memory there is of no use. And definitely the use of array as a dynamic list is not efficient in terms of memory. This kind of implementation is not efficient in terms of memory. This leads us to think, can we have a data structure that will give us a dynamic list and use the memory more efficiently? We have one data structure that gives us good utilization of the memory, and this data structure is linked list, and we will study about the linked lists in the next lesson. So that's it for this lesson. Thanks for watching. In this lesson, we will introduce you to linked list data structure. In our previous lesson, we tried to implement a dynamic list using arrays, and we had some issues there. it was not most efficient in terms of memory usage, in terms of memory consumption. When we use arrays, we have some limitations. To be able to understand linked list well, we need to understand these limitations. So I'm going to tell you a simple story to help you understand this. Let us say this is computer's memory and each partition here is 1 byte of memory. Now as we know, each byte of memory has an address. We are showing only a section of the memory, that's why it is extending towards the bottom and the top. Let's say the address increases from bottom to top. So if this byte is address 200, the next byte would be address 201 and next byte would be address 202 and so on. What I want to do is I want to draw this memory from left to right horizontally instead of drawing it from bottom to top like this. This looks better. Let's say this byte here is address 200 and as we go towards the right the address increases. So this is like 201 and we go on like 202, 203 and so on. It doesn't really matter whether we show memory from bottom to top or left to right. These are just logical ways to look at the memory. So coming back to our story, memory is a crucial resource and all the applications keep asking for it. So Mr. Computer has given this job of managing the memory to one of his components, to one of his guys, who he calls the memory manager. Now this guy keeps track of what part of the memory is free and what part of the memory is allocated, and anyone who needs memory to store something needs to talk to this guy. Albert is our programmer and he is building an application. He needs to store some data in the memory, so he needs to talk to the memory manager. He can talk to the memory manager in a high level language like C. Let us say that he is using C to talk to the memory manager. First he wants to store an integer in the memory. So he communicates this to memory manager by declaring an integer variable, something like this. The memory manager sees this declaration and he says that okay, you need to store an integer variable, so I need to give you 4 bytes of memory because integer variable is stored in 4 bytes in a typical architecture, and let us say in this architecture it is stored in 4 bytes. So the memory manager looks for 4 bytes of free space in the memory and assigns it or allocates it for variable x. Address of a block of memory is the address of the first byte in the memory. So let us say this first byte of memory here is at address 217. So variable x is at address 217. So memory manager kind of communicates it back to Albert that hey, I have assigned address 217 for your variable x. You can store whatever you want there. And Albert can fill in any data into this variable. Now Albert needs to store a list of integers, a list of numbers. And he thinks that the maximum number of integers in this list will be 4. So he asks the memory manager for an integer array of size 4 named A. Now array is always stored in memory as one contiguous block of memory. So memory manager is like, okay, I need to look for a block of memory of 16 bytes for this variable, this array A. So the memory manager allocates this block starting address 201 and ending address 216 for this variable A, which is an array of 4 integers. Because array is stored as one contiguous block of memory and memory manager conveys the starting address of this block, whenever Albert tries to access any of the elements in the array, let's say he tries to write some value at the 4th element in the array, which he accesses as A3, Albert's application knows where to write this particular value because it knows the base address, the starting address of the block A, the array A, and from base address using the index, which is 3 here, it calculates the address of A3. So it knows that A3 is at address 213. So to access any of the elements in the array, the application takes constant time. And this is one awesome thing about arrays, that irrespective of the size of the arrays, an application can access any of the elements in the array in constant time. Now let's say Albert uses this array of 4 integers to store his list. So I'll fill in some values here at these positions. Let's say this is 8, this is 2, this is 6, this is 5, this is 4. Now Albert at some point feels that, okay, I need to have one more element in this list. Now he has declared an array of size 4 and he wants to add a 5th element in the array. So he asks the memory manager that, hey, I want to extend my array A. Is it possible to do so? I want to extend the same block. And the memory manager is like, when I allocate memory for an array, I do not expect that you will ask for an extension. So I use whatever memory is available adjacent to that block for other variables. In some cases, I may extend the same block, but in this case, I have an element and a variable x next to your block, so I cannot give you an extension. So Albert is like, what all options do I have? Memory manager is like, you can tell me the new size and I can recreate a new block at some new address, and we will have to copy all the elements from the previous block to the new block. So Albert says that, okay, let's do it. But the memory manager is like, you still need to give me the size of the new block. Albert thinks that this time he'll give a really large size for the new array or the new block so that it does not fill up. This new block starting address 224 is allocated. Albert asks memory manager to free the previous block, and this is some cost. He has to copy all the elements, all the numbers from the previous block into the new block, and now he can add one more element to this list. And he has kept his array large this time, just in case he needs more numbers in the list. So the only option that Albert had was to create A as an entirely new block, as an entirely new array. And Albert is still feeling bad because if the list is too small, he is not using some part of the array, and so memory is getting wasted. And if the list again grows too much, he will again have to create a new array, a new block, and he will again have to copy all the elements from the previous block into the new block. Albert is desperately seeking a solution to this problem, and the solution to this problem is a data structure named linked list. So let us now try to understand linked list data structure and see how it solves Albert's problem. What Albert can do is that instead of asking the memory manager for an array, which will be one large contiguous block of memory, he can ask memory for one unit of data at a time, for one element at a time in a separate request. I'm cleaning up the memory here. Once again, let's say Albert wants to store this list of 4 integers in the memory. What if he requests memory for one integer at a time? So first he pings memory manager for some memory to store number 6. Memory manager will be like, okay, you need space to store an integer. So you get this block of 4 bytes at address 204. So Albert can store number 6 here. Now Albert makes another request, a separate request for number 5. Let's say he gets this block starting address 217 for number 5. Because he makes a separate request, he may or may not get memory adjacent to number 6. Higher probabilities that he will not get an adjacent memory location. So similarly, Albert makes separate requests for number 4 and 2. So let's say he gets these 2 blocks at address 232 and 242 respectively for numbers 4 and 2. So as you can see, when Albert makes separate requests for each integer, instead of getting one contiguous block of memory, he gets these disjoint, non-contiguous blocks of memory. So we need to store some more information here. We need to store the information that this is the first element in the list and this is the second element in this list. So we need to link these blocks together somehow. With an array, it was very simple. We had one contiguous block of memory, so we knew where a particular element is by calculating its address using the starting address of the block and the position of the element in the array. But here we need to store the information that this is the first block which stores the first element, and this is the second block which stores the second element, and so on. To link these blocks together and to store the information that this is the first block in the list and this is the second block in the list, what we can do is that we can store some extra information with each block. So what if we can have 2 parts in each block, something like this, and in one part of the block we store the data or the value, and in the other part of the block we store the address of the next block. In this example, in the first block, the address part would be 217, the address of the next block that stores 5, and in this next block or the second block the address part would be 232. In the block at address 232 we will store the address 242, the address of the next block that stores number 2, and the block at 242 is the last block. There is no next block after this, so in the address part we can have address as 0. 0 is invalid address. 0 can be used to mark that this is the end of the list. There is no link to the next node or next block after this particular block. So Albert now actually has to request memory manager for a block of memory that will store two variables. One, an integer variable that will store the value of our element, and one, a pointer variable that will store the address of the next block or the next node in the list. In C, he can define a type named node like this. He will have two fields in the node, one to store the data. This field will be an integer, and one more field to store the address of the next node in the list. So Albert will ask memory for a node from the memory manager, and the memory manager will be like, okay, you need a node that needs 4 bytes for an integer variable and 4 more bytes for the pointer variable that will store the address. Pointer variable also in a typical architecture is stored in 4 bytes. So now memory manager gives us a block of 8 bytes, and we call this block a node. Now notice that the second field in the node structure is node star, which means pointer to node. So this field will only store an address of the next node in the list. So if we store the list like this in the memory as these non-contiguous nodes connected to each other, then this is a linked list data structure. Logical view of the linked list data structure will be something like this. Data is stored in these nodes, and each node stores the data as well as the link to the next node. So each node kind of points to the next node. The first node is also called the head node, and the only information about the list that we keep all the time is address of the head node or address of the first node. So address of the head node kind of gives us access to the complete list. The address in the last node is null or 0, which means that the last node does not point to any other node. Now if we want to traverse the linked list, the only way to do it is we start at the head, we go to the first guy, and then we ask the first guy the address of the next guy, address of the next node, and then we go to the next node and ask the address of the next node. And this is the only way to access the elements in the linked list. If we want to insert a node in the linked list, let's say we want to add number 3 at the end of the linked list, then all we need to do is first create a node in the linked list. Create a node independently and separately. It will get some memory location. So we created this node with value 3. Now all we need to do is fill the address properly, adjust these links properly. So the address of this particular node will be filled in this node with value 2, and this node, the address part can be null, so it is the last node, it does not point to any other node. Let's also show this these nodes in the memory here. So I've written the address of each node in brown at top of these nodes, and I've also filled in this address field of each node. Let's say the node for value 3 gets address 252. So this is how things will be in the memory, and this is how the logical view will be. The linked list is always identified by the address of the first node, and unlike arrays, we cannot access any of the elements in constant time. In the case of arrays, using the starting address of the block of memory and using the position of the element in the list, we could calculate the address of the element. But in this case, we have to start at the head, and we have to ask this element for next element, and then ask the next element who is your next. It's like playing treasure hunt. You go to the first guy, and then you get the address for the second guy, and then you go to the second guy and you get the address for the third guy. So the time taken to access elements will be proportional to the size of the list. Let's say the size of the list is n. There are n elements in the list. In the worst case, to traverse the last element, you will go through all the elements. So time taken to access elements is proportional to n, or in other words, we say that this operation will cost us, or rather the time complexity of this operation is big O of n. Insertion into the list. We can insert anywhere in the list. We first need to create a node and just adjust these links properly. Like say I want 10 at third position in the list, so all we need to do is create a node, store the value 10 in the data part, something like this. Let's say we get the node 10 at address 310. So we will adjust the address field in the second node to point to this node with address 310, and this node will point to the node with value 4. Now to insert also, we will have to traverse the list and go to that particular position, and so this will be big O of n again in terms of time complexity. The only thing is that the insertion will be a simple operation. We will not have to do all the shifts as we had to do in an array. To insert something in between, we had to shift all the elements by one position towards higher indices. Similarly, to delete something from this list will also be on. So we can see some good things about linked list. There is no extra use of memory in the sense that some memory is unused. We are using some extra memory. We are using some extra memory to store the addresses, but we have the benefit that we create nodes as and when we want, and we can also free the nodes as and when we want. We do not have to guess the size of the list beforehand like in the case of arrays. We will discuss all the operations on linked list and the cost of these operations as well as comparison with arrays in our next lessons. We will also be implementing linked list in C or C++. So this is all for a basic introduction to linked list. Thanks for watching. In our previous lesson, we introduced you to linked list data structure, and we saw how linked lists solve some of the problems that we have with arrays. So now the obvious question would be, which one is better, an array or a linked list? Well, there is no such thing as one data structure is better than another data structure. One data structure may be really good for one kind of requirement, while another data structure can be really good for another kind of requirement. So it all depends upon factors like what is the most frequent operation that you want to perform with the data structure, or what is the size of the data, and there can be other factors as well. So in this lesson, we will compare these two data structures based on some parameters, based on the cost of operations that we have with these data structures. So all in all, we will comparatively study the advantages and disadvantages and try to understand in which scenario we should use an array and in which scenario we should use a linked list. So I will draw two columns here, one for array and another for linked list. And the first parameter that we want to talk about is the cost of accessing an element. Irrespective of the size of an array, it takes constant time to access an element in the array. This is because an array is stored as one contiguous block of memory. So if we know the starting address or the base address of this block of memory, let us say what we have here is an integer array and the base address is 200. The first byte in this block is at address 200. Then let's say if we want to calculate the address of element at index I, then it will be equal to 200 plus I into size of an integer in bytes. So size of an integer in bytes is typically 4 bytes. So it will be 200 plus 4 into I. So if 0th element is at address 200, if we want to calculate the address for element at index 6, it will be 200 plus 6 into 4, which will be equal to 224. So knowing address of any element in an array is just this calculation for our application. In terms of big O notation, constant time is also called big O of 1. So accessing an element in an array is big O of 1 in terms of time complexity. If you are not aware of big O notation, check the description of this video for a tutorial on time complexity analysis. Now in a linked list, data is not stored in a contiguous block of memory. So if we have a linked list, something like this, let's say we have a linked list of integers here, then we have multiple blocks of memory at different addresses. Each block in the linked list is called a node, and each node has two fields, one to store the data and one to store the address of the next node. So we call the second field the link field. The only information that we keep with us about a linked list is the address of the first node, which we also call the head node. And this is what we keep passing to all the functions also, the address of the head node. To access an element in the linked list at a particular position, we first need to start at the head node or the first node. And at the first node, we need to see the address of the second node, and then we go to the second node and see the address of the third node. In the worst case, to access the last element in the list, we will be traversing all the nodes in the list. In the average case, we will be accessing the middle element maybe. So if n is the size of the linked list, n is the number of elements in the linked list, then we will traverse n by 2 elements. So the time taken in the average case also is proportional to number of elements in the linked list. So we can say that the time complexity in average case is big O of n. So on this parameter, cost of accessing an element, array scores heavily over a linked list. So if you have a requirement where you want to access elements in the list all the time, then definitely array is a better choice. Now the second parameter that we want to talk about is memory requirement or memory usage. With an array, we need to know the size of the array before creating it, because array is created as one contiguous block of memory. So array is of fixed size. What we typically do is we create a large enough array, and some part of the array stores our list and some part of the array is vacant or empty, so that we can add more elements in the list. For example, we have an array of 7 integers here, and we have only 3 integers in the list. Rest 4 positions are unused. There would be some garbage value there. With linked list, let's say we have this linked list of integers. There is no unused memory. We ask memory for one node at a time, so we do not keep any reserved space, but we use extra memory for pointer variables. And this extra memory requirement for pointer variables in a linked list cannot be ignored. In a typical architecture, let's say, integer is stored in 4 bytes and pointer variable also takes 4 bytes. So if you see, the memory requirement for this array of 7 integers is 28 bytes, and the memory requirement for this linked list would be 8 into 3, where 8 is the size of each node, 4 for integer and 4 bytes for the pointer variable. So this is also 24 bytes. If we add one more element to the list in the array, we will just use one more position, while in linked list we will create one more node and will take another 8 bytes, so this will be 32 bytes. Linked list would fetch us a lot of advantage if the data part is large in size. So in this case we had a linked list of integers, so integer is only 4 bytes. What if we had a linked list in which a data part was some complex type that took 16 bytes? So 4 bytes for the link and 16 bytes for the data. Each node would have been 20 bytes. An array of 7 elements for 16 bytes of data would be 16 byte for each element would be 112 bytes, and linked list of 4 would be only 80 bytes. So it all depends. If the data part for the list takes a lot of memory, linked list will definitely consume lot less memory. Otherwise, it depends what strategy we are choosing to decide the size of the array. At any time, how much array we keep unused. Now, one more point with memory allocation. Because arrays are created as one contiguous block of memory, sometimes when we may want to create a really large array, then maybe memory may not be available as one large block. But if we are using linked list, memory may be available as multiple small blocks. So we will have this problem of fragmentation in the memory. Sometimes we may get many small units of memory but may not get one large block of memory. This may be a rare phenomenon, but this is a possibility. So this is also where linked list scores. Because arrays have fixed size, once array gets filled and we need more memory, then there is no other option than to create a new array of larger size and copy the content from the previous array into the new array. So this is also one cost which is not there with linked list. So we need to keep these constraints and these requirements in mind when we want to decide for one of these data structures for our requirement. Now the third parameter that we want to talk about is cost of inserting an element in the list. Remember, when we are talking about arrays here, we are also talking about the possible use of array as dynamic list. So there can be three scenarios in insertion. First scenario will be when we want to insert an element at the beginning of the list. Let's say we want to insert number 3 at the beginning of the list. In the case of arrays, we will have to shift each element by one position towards the higher index. So the time taken will be proportional to the size of the list. So this will be big O of n. Let's say n is the size of the list. This will be big O of n in terms of time complexity. In the case of linked list, inserting an element in the beginning will mean only creating a new node and adjusting the head pointer and the link of this new node. So the time taken will not depend upon the size of the list, it will be constant. So for linked list, inserting an element at the beginning is big O of 1 in terms of time complexity. Inserting an element at end for an array, let's say we are talking about dynamic array, a dynamic list in which we create a new array if it gets filled. If there is space in the array, we just write to the next higher index of the list. So it will be constant time. So time complexity is O1 if array is not full. If array is full, we will have to create a new array and copy all the previous content into new array, which will take O(n) time, where n is the size of the list. In the case of linked list, adding an element, inserting an element at the end will mean traversing the whole list and then creating a new node and adjusting the links. So time taken will be proportional to n. I'll use this color coding for linked list. Here n is the number of elements in the list. Now the third case would be when we want to insert in the middle of the list at some nth position or maybe some ith position. Again, in the case of arrays, we will have to shift elements. For the average case, we may want to insert at the mid position in the array. So we will have to shift n by 2 elements, where n is the number of elements in the list. So the time taken is definitely proportional to n in average case. So complexity will be big O of n. For linked list also, we will have to traverse till that position and then only we can adjust the links. Even though we will not have any shifting, we will have to traverse till that point, and in the average case, time taken will be proportional to n and the time complexity will be big O of n. If you can see, deleting an element will also have these three scenarios, and the time complexity for deleting for these three scenarios will also be the same. And the final point, the final parameter that I want to talk about is which one is easy to use and implement. And array definitely is a lot easier to use. Linked list implementation, especially in C or C++, is more prone to errors like segmentation fault and memory leak. It takes good care to work with linked list. So this was arrays versus linked list. In our next lesson, we will implement linked list in C or C++. We will get our hands dirty with some real code. So this is it for this lesson. Thanks for watching. In our previous lessons, we described linked list. We saw the cost of various operations in linked list, and we also compared linked list with arrays. So now let us implement linked list. The implementation will be pretty similar in C and C++. There will be slight differences that we will discuss. The prerequisite for this lesson is that you should have a working knowledge of pointers in C, C++, and you should also know the concept of dynamic memory allocation. If you want to refresh any of these concepts, check the description of this video for additional resources. Okay, so let's get started. As we know, in a linked list, data is stored in multiple non-contiguous blocks of memory, and we call each block of memory a node in the linked list. So let me first draw a linked list here. So we have a linked list of integers here with 3 nodes. As we know, each node has 2 fields or 2 parts, one to store the data and another to store the address of the next node, what we can also call link to the next node. So let's say the address of the first node is 200 and address of the second node is 100 and the address of the third node is 300 for this linked list. This is only a logical view of the linked list. So the address part of the first node will be 100, the address of the second node, and we will have 300 here. The address part of the last node will be null, which is only a synonym or macro for address 0. 0 is an invalid address. A pointer variable equal to 0 or null with address 0 or null means that the pointer variable does not point to a valid memory location. The memory block, the address of the memory block allocated to each of the nodes is totally random. There is no relation. It's not a guarantee that the addresses will be in increasing order or decreasing order or adjacent to each other. So that's why we need to keep these links. Now the identity of the linked list that we always keep with us is the address of the first node, what we also call the head node. So we keep another variable that will be of type pointer to node, and this guy will store the address of the first node, and we can name this pointer variable whatever. Let's say this pointer variable is named A. The name of this particular pointer variable that points to the head node or the first node can also be interpreted as the name for the linked list also, because this is the only identity of the linked list that we keep with us all the time. So let us now see how this logical view can be mapped to a real program in C or C++. In our program, node will be a data type that will have 2 fields, one to store the data and another to store the address. In C, we can define such a data type as structure. So let's say we define a structure named node with 2 fields. First field to store the data. The type of the data here is integer, so this will be node for a linked list of integers. If we wanted a linked list of say double, this data type would be double. The second field will be pointer to node, struct node star. We can name this link or we can name this next or whatever. This is C style of declaring node star or pointer to node. If this was C++, we could simply write node star. I would write it this way, the C++ way. It looks better to me. In our logical view here, this variable A is of type node star or pointer to node. Each of these 3 rectangles with 2 fields are of type node, and this field in the node, the first field is of type integer and the second field is of type pointer to node or node star. It is important to know which one is what in the logical view. We should have this visualization before we go on to implement linked list. Okay, so let us now create this particular linked list of integers that we are showing here through our code. To be able to do so, we will have to implement 2 operations. One to insert a node into the linked list, one operation to insert a node in the linked list, and another operation to traverse the linked list. But before that, the first thing that we want to do is that we want to declare a pointer to the head node, a variable that will store the address of the head node. For the sake of clarity, I'll write head node here. So I have declared a pointer to node named A. Initially, when the list is empty, when there is no element in the list, this pointer should point nowhere. So we write a statement something like A is equal to null to say the same. With these 2 statements, what we have done is we have created a pointer to node named A, and this pointer points nowhere, so the list is empty. Now let's say we want to insert a node in this list. So what we do is we first create a node. Creating a node is nothing but creating a memory block to store a node. In C, we use the function malloc to create a memory block. As argument, we pass the number of bytes that we want in the block. So we say that give me a memory block that will be equal to the size of a node. So this call to malloc will create a memory block. This is a dynamically allocated memory allocated during runtime, and the only way to work with this kind of memory is through reference to this memory location through pointers. Let us assume that this memory block assigned here is at address 200. Now malloc returns a void pointer that gives us the address of assigned memory block. So we need to collect it in some variable. So let's say we create a variable named temp, which is pointer to node. So we can collect the return of malloc, the address in this particular variable. We will need a typecasting here because malloc returns void pointer and we are having temp as pointer to node. So now we have created one node in the memory. And now what we need to do is fill in the data in this particular node and adjust the links, which will mean writing the correct address in the variable a and the link field of this newly created node. To do so, we will have to dereference this particular pointer variable that we just created. As we know, if we put an asterisk sign in front of the pointer variable, we mean dereferencing it to modify the value at that particular address. Now in this case, we have a node which has two fields. So once we dereference, if we want to access each of the fields, we need to put something like a dot data here to access the data and a dot link to write to the link field. So we will write a statement like this to fill in value 2 here, and we have this temp variable pointing to this right now, and the link part of this newly created node should be null because this is the first and the last node. And the final thing that we need to do is write the address of this newly created node in A. So we will write something like A is equal to temp. Okay, temp was to temporarily store the address of the node till the time we had not fixed all the links properly. We can now use temp for some other purpose. Our linked list is intact now. It has one node. These two lines that we have written here for dereferencing and writing the values into the new node, there is alternate syntax for this. Instead of writing something like start temp bracketed dot data, we could also write temp followed by this arrow and data. We will have two characters to make this arrow, one hyphen and one this right angular bracket, right angular brace. So we can write something like this, and the same thing below we can write something like this. To create a memory block in C++, we can use malloc as well as we can use the new operator. So in C++ it gets very simple. We could simply write node start temp is equal to new node like this, and we would mean the same thing. This is a lot cleaner, and new operator is always preferred over malloc. So if you're using C++, new is recommended. So far through our program, we created an empty list by creating this pointer to the head node and assigning the value null to it initially. Then we created a node and we added this first node in this linked list. When the list is empty and we want to insert a node, the logic is pretty straightforward. When the list is not empty, we may want to insert a node at the beginning of the list, or we may want to insert a node at the end of the list, or we may even want to insert a node somewhere in the middle of the list at a particular position. We will write separate functions and routines for these different kind of insertions, and we will see running code in a compiler in our coming lessons. Let's just talk about the logic here in this whatever unstructured code I have right now. So I want to write a code to insert 2 more nodes each time at the end of the list. We actually want to create the linked list with 3 nodes having values 2, 4 and 6. That was our initial example in the beginning. Okay, so let us add 2 more nodes with values 4 and 6 into this linked list. At this stage in our code, we already have a variable temp which is pointing to this particular node. We will create a new node and use the same variable name to collect the address of this new node. So we will write a statement like this. So a new node is created and temp now stores the address of this new node. which is located at address 100 here. Once again, we can set the data, and then because this is going to be the last node, we need to set the link as null. Now all we need to do is build the link of this particular node, write the address of this newly created node into the address field of this last node. To do so, we will have to traverse the list and we will have to go to the end of the list. To do so, we will write something like this. We can create a new variable temp1 which will be pointed to node, and initially we can point to the head node, point this variable to the head node by a statement like this. We can write a loop like this. Now this is generic logic to reach the end of the list. It will not be so clear if we see this logic with only one node as we have in this example. Let's draw a list with multiple nodes. So we are pointing temp1 to the first node here, and if the link part of this node is null, we are at the last node, else we can move to the next node. So temp1 equal temp1 dot link will get us to the next node, and we will go on till we reach the last node. For the last node, this particular condition temp1 dot link not equal null will be false because the link part will be null, and we will exit this while loop. So this is our code logic for traversal of the list all the way till end. If we want to print the elements in the list, we will write something like this, and we will write print temp.data inside this while loop. But right now we want to insert at the end of the list, and we are only traversing the list to reach the last node. There is one more thing that I want to point out. We are using this variable temp1 and initially storing the address in A. We are not doing something like A equal A dot link and using the variable A itself to traverse the list, because if we modify A, we will lose on the address of the head node. So A is never modified. The address of the head node, whatever variable stores the address of the head node, is never modified. Only these temporary variables are modified to traverse the list. So finally, after all this, we will write a statement like temp1.link is equal to temp. Temp1 is pointing here. So now this address part is updated and this link is built. So we have two nodes now in the list. Once again, when we want to insert node with number 6 in this list, we will have to create a new node by this logic. Then we will have to traverse the list by this logic. So we will point temp1 here first, and then the loop will move the temp1 to the end. Let's say this new block is at address 300, so this last line finally will adjust the link of the node at address 100. To insert a node at the end, there is one logic in these 4 lines if the list is empty, and there is another logic in these remaining lines if the list is not empty. Ideally, we will be writing all this logic in a function. We will do that in our coming lessons. We will implement separate methods to print all the nodes in a linked list, and to insert a node at the end, we will implement a separate method to insert a node at the beginning of the list and at a particular position in the list. So this is all for this lesson. Thanks for watching. In our previous lesson, we saw how we can map the logical view of a linked list into a C or C++ program. We saw how we can implement two basic operations, one traversal of the linked list and another inserting a node at the end of the linked list. In this lesson, we will see a running code that will insert a node at the beginning of the linked list. So let's get started. I will write a C program here. The first thing that we want to do in our program is that we want to define a node. A node will be a structure in C. It will have two fields, one to store the data. Let's say we want to create a linked list of integers, so our data type will be integer. If we wanted to create a linked list of characters, then our type would be character here. So we will have another field that will be pointer to node that will store the address of the next node. We can name this variable link, or some people also like to name this variable next because it sounds more intuitive. This variable will store the address of the next node in the linked list. In C, whenever we have to declare node or pointer to node, we will have to write struct node or struct node star. In C++, we will have to write only node star, and that's one difference. Okay, so this is the definition of our node. Now to create a linked list, we will have to create a variable that will be pointer to node and that will store the address of the first node in the linked list, what we also call the head node. So I will create a pointer to node here, struct node star. We can name this variable whatever. Often for the sake of understanding, we name this variable head. Now I have declared this variable as a global variable. I have not declared this variable inside any function, and I'll come back to why I'm doing so. Now I'll write the main method. This is the entry point to my program. The first thing that I want to do is I want to say head is equal to null, which will mean that this pointer variable points nowhere. So right now the list is empty. So far what we have done here in our code is that we have created a global variable named head, which is of type pointer to node, and the value in this pointer variable is null. So far the list is empty. Now what I want to do in my program is that I want to ask the user to input some numbers, and I want to insert all these numbers into the linked list. So I'll print something like how many numbers. Let's say the user wants to input n numbers, so I'll collect this number in this variable n, and then I'll define another variable I to run the loop. And so I'm running a loop here. If it was C++, I could declare this integer variable right here inside the loop. Now I'll write a print statement like this, and I'll define another variable x, and each time I'll take this variable x as input from the user. And now I will insert this particular number x, this particular integer x, into the linked list by making a call to the method insert. And then each time we insert, we will print all the nodes in the linked list, the value of all the nodes in the linked list, by calling a function named print. There will be no argument to this function print. Of course, we need to implement these two functions, insert and print. Let me first write down the definition of these two functions. So let us implement these two functions, insert and print. Let us first implement the function insert, that will insert a node at the beginning of the linked list. Now in the insert function, what we need to do is we first need to create a node. In C, we can create a node using malloc function. We have talked about this earlier. Malloc returns a pointer to the starting address of the memory block. We are having to typecast here because malloc returns a void pointer, and we need a pointer to node, a variable that is pointer to node. And then only if we dereference using an asterisk sign, then we will be able to access the fields of the node. So the data part will be x, and we have an alternate syntax for this particular syntax. We could simply write something like temp and this arrow, and it will mean the same thing, and this is more common. With these two lines in the insert function, all we are doing is we are creating a node. Let's say we get this node, and let's assume that the address that we get for this node is 100. Now there is a variable temp where we are storing the address. We can do one thing. Whenever we create a node, we can set data to whatever we want to set, and we can set the link field initially to null, and if needed we can modify the link field. So I'll write one more statement, temp.next is equal to null. Remember, temp is a pointer variable here, and we are dereferencing the pointer variable to modify the value at this particular node. Temp will also take some space in the memory. That's why I have shown this rectangular block for both the pointer variables head and temp. And node has two parts, one for the pointer variables and one for the data. So this part, the link part, is null. We can either write null here or we can write it like this. It's the same thing. Logically it means the same. Now if we want to insert this node in the beginning of the list, there can be two scenarios. One, when the list is empty, like in this case. So the only thing that we need to do is we need to point head to this particular node instead of pointing to null. So I will write a statement like head is equal to temp, and the value in head now will be address 100. And that's what we mean when we say a pointer variable points to a particular node. We store the address of that node. So this is our linked list after we insert the first node. Let us now see what we can do to insert a node at the beginning if the list is not empty, like what we have right now. Once again, we can create a node, fill in the value x here that is passed as argument. Initially we may set the link field as null, and let's say this node gets address 150 in the memory, and we have this variable temp through which we are referencing this particular memory block. Now unlike the previous case, if we just set head is equal to temp, This is not good enough because we also need to build this link. We need to set the next or the link of the newly created node to whatever the previous head was. So what we can do is we can write something like, if head is not equal to null, or if the list is not empty, first set temp.next equal head. So we first build this link. The address here will be 100, and then we say head equal temp. So we cut this link and point head to this newly created node, and this is our modified linked list after insertion of this second node at the beginning of the list. Now one final thing here, this particular line, the third line, temp.next equal null, this is getting used only when the list is empty. If you see, when the list is empty, head is already null. So we can avoid writing two statements. We can simply write this one statement, temp.next equal head, and this will also cover the scenario when the list is empty. Now the only thing remaining in this program to get this running is the implementation of this print function. So let us implement this print function. What I will do here is I'll create a local variable which is pointer to node named temp, and I need to write struct node here. I keep missing this. In C you need to write it like this, and I want to set this as address of the head node. So this global variable has the address of the head node. Now I want to traverse the linked list, so I will write a loop like this. While temp is not equal to null, I'll keep going to the next node using this statement, temp is equal to temp.next, and at each stage I'll print the value in that node as temp.data. Now I'll write two more print, one outside this while loop and one outside after this while loop to print an end of line. Now why did we use a temporary variable? Because we do not want to modify head, because we will lose the reference of the first node. So first we collect the address in head in another temporary variable, and we are modifying the addresses in this temporary variable using temp is equal to temp.next to traverse the list. Let us now run this program and see what happens. So this is asking how many numbers you want to insert in the list. Let's say we want to insert 5 numbers. Initially the list is empty. Let's say the first number that we want to insert is 2. At each stage we are printing the list. So the list is now 2. The first element and the last element is 2. We will insert another number. The list is now 5. 5 is inserted at the beginning of the list. Again we inserted 8, and 8 is also inserted at the beginning of the list. Okay, let's insert number 1. The list is now 1852. And finally I inserted number 10. So the final list is 101852. This seems to be working. Now if we were writing this code in C++, we could have done a couple of things. We could have written a class and organized the code in an object-oriented manner. We could also have used new operator in place of the malloc function. Now coming back to the fact that we have declared this head as global variable, what if this was not a global variable? This was declared inside this main function as a local variable. So I'll remove this global declaration. Now this head will not be accessible in other functions, so we need to pass address of the first node as argument to other functions, to both these functions, print and insert. So to this print method we will pass, let's say we name this argument as head. We can name this argument as head or a or temp or whatever. If we name this argument as head, this head in print will be a local variable of print and will not be this head in main. These two heads will be different. These two variables will be different. When the main function calls print passing its head, then the value in this particular head in the main function is copied to this another head in the print function. So now in the print function we may not use this temp variable. What we can do is we can use this variable head itself to traverse the list, and this should be good. We are not modifying this head here in the main. Similarly to the insert function, we will have to pass the address of the first node, and this head again is just a copy. This is again a local variable. So after we modify the linked list, the head in main method should also be modified. There are two ways to do it. One, we can pass the pointer to node as return from this method. So in the main method, insert function will take another argument, head, and we will have to collect the return into head again so that it is modified. Now this code will work fine. Oops, I forgot to write a return here, return head. And we can run this program like before. We can give all the values and see that the list is building up correctly. There was another way of doing this. Instead of asking this insert function to return the address of head, we could have passed this particular variable head by reference. So we could have passed insert ampersand head. Head is already a pointer to node. So in the insert function, we will have to receive pointer to pointer, node star star. And to avoid confusion, let's name this variable something else. This time, let's name this pointer to head. So to get head, we will have to write something like, we will have to dereference this particular variable and write asterisk pointer to head everywhere. And the return type will be void. Sometimes we want to name this variable as head, this local variable as head. Doesn't matter, but we will have to take care of using it properly. Now this code will also work. As you can see here, we can insert nodes, and this seems to be going well. If you do not understand these concepts of scope, you can refer to the description of this video for additional resources. So this was inserting a node at the beginning of the linked list. Thanks for watching. In our previous lesson, we had written code to insert a node at the beginning of the linked list. Now in this lesson, we will write program to insert a node at any given position in the linked list. So let me first explain the problem in a logical view. Let's say we have a linked list of integers here. There are 3 nodes in this linked list. Let us say they are at addresses 200, 100 and 250 respectively in the memory, and we have a variable head, and that is pointer to node that stores the address of the first node in the list. Now let us say we number these nodes, we number these positions on a 1 based index. So this is the first node in the list, and this is the second node, and this is the third node, and we want to write a function insert that will take the data to be inserted in the list and the position at which we want to insert this particular data. So we will be inserting a node at that particular position with this data. There will be a couple of scenarios. The list could be empty, so this variable head will be null, or this argument being passed to the insert function, the position n, could be an invalid position. For example, 5 is an invalid position here for this linked list. The maximum possible position at which we can insert a node in this list will be 4. If we want to insert at position 1, we want to insert at the beginning, and if we want to insert at position 4, we want to insert at end. So our insert function should gracefully handle all these scenarios. Let us assume, for the sake of simplicity, for the sake of simplifying our implementation, that we always give a valid position. We will always give a valid position so that we do not have to handle the error condition in case of invalid position. The implementation logic for this function will be pretty straightforward. We will first create a node. Let's say in this example we want to insert a node with value 8 at third position in the list. So I'll set the data here in the node. The data part is 8. Now to insert a node at the nth position, we will first have to go to the n-1th node. In this case, n is equal to 3, so we will go to the second node. Now the first thing that we will have to do is we will have to set the link field of this newly created node equal to the link field of this n-1th node. So we will have to build this link. Let's say the address that we get for this newly created node is 150. Once we build this link, we can break this link and set the link of this newly created node as address of this, set the link of this n-1th node as address of this newly created node. We may have special cases in our implementation, like the list may be empty, or maybe we may want to insert a node at the beginning. Let's say we will take care of special cases, if any, in our actual implementation. So now let's move on to implement this particular function in our program. In my C program, the first thing that I need to do is I want to define a node. So node will be a structure. We have seen this earlier. So node has these two fields, one data of type integer and another next of type pointer to node. Now to create a linked list, the first thing that I need to create is a pointer to node that will always store the address of the first node or the head node in the linked list. So I will create a struct node star. Let's name this variable head. And once again, I have created this variable as a global variable. To understand linked list implementation, we need to understand what goes where, what variable sits in what section of the memory, and what is the scope of these variables, what goes in the stack section of the memory and what goes in the heap section of the memory. So this time, as we write this code, we will see what goes where. In the main method, first I'll set this head as null to say that initially the list is empty. So let us now see what has gone where so far in our program, in what section of the memory. And the memory that is allocated to our program or application is typically divided into these four parts or these four sections. We have talked about this in our lesson on dynamic memory allocation. There is a link to our lesson on dynamic memory allocation in the description of this video. I'll quickly talk about what these sections are. One section of the application's memory is used to store all the instructions that need to be executed. Another section is allocated to store the global variables that live for the entire lifetime of the program, of the application. One section of the memory, which is called stack, is used to store all the information about function call executions, to store all the local variables. And these three sections that we talked about are fixed in size. Their size is decided at compile time. The last section that we call heap or free store is not fixed, and we can request memory from the heap during runtime, and that's what we do when we use malloc or new operator. Now I have drawn these three sections of the memory: stack, heap, and the section to store the global variables. In our program, we have declared a global variable named head, which is pointer to node. So it will go and sit here, and this variable is like anyone can access it. Initially, value here is null. Now in my program, what I want to do is I first want to define two functions, insert, and this function should take two arguments: data and the position at which I want to insert a node, and insert that particular node at that position, insert data at that position in the list, and another function print that will simply print all the numbers in the linked list. Now in the main method, I want to make a sequence of function calls. First I want to insert number 2. The list is empty right now, so I can only insert at position 1. So after this, insert list will be having this one number, this particular number 2, and let's say again I want to insert number 3 at position 2. So this will be our list after this insertion, and I will make two more insertions, and finally I'll print the list. So this is my main method. I could have also asked a user to input a number and position, but let's say we go this way this time. Now let us first implement insert. I'll move this print above. So the first thing that I want to do in this method is I want to create a node. So I will make a call to malloc. In C++, we can simply write a new node for this call to malloc, and this looks a lot cleaner. Let's go C++ way this time. Now what I can do is I can first set the data field and set the link initially as null. I have named this variable temp1 because I want to use another temp variable in this function. I'll come to that in a while. We first need to handle one special case when we want to insert at the head, when we want to insert at the first position. So if n is equal to 1, we simply want to set the link field of the newly created node as whatever the existing head is, and then adjust this variable to point to the new head, which will be this newly created node, and we will be done at this stage, so we will not execute any further and return from this function. If you can see, this will work even when the list is empty because the head will be null in that case. I'll show a simulation in the memory in a while, so hold on till then. Things will be pretty clear to you after that. Now for all other cases, we will first need to go to the n-1th node, as we had discussed in our logic initially. So what I'll do is I'll create another pointer to node, name this variable temp2, and we will start at the head, and then we will run a loop and go to the n-1th node, something like this. We will run the loop n-2 times because right now we are pointing to head, which is the first node. So if we do this temp2 equal temp2 dot next n-2 times, we will be pointing temp2 to n-1th node. And now the first thing that we need to do is set the next or the link field of newly created node as the link field of this n-1th node, and then we can adjust the link of this n-1th node to point to our newly created node. And now I'm writing this print here. I've written this print here. We have used a temporary variable, a temporary pointer to node, initially pointed it to head, and we have traversed the whole list. Okay, so let us now run this program and see what happens. We are getting this output, which seems to be correct. The list should be 4, 5, 2, 3 in this order. Now I have this code. I'll run through this code and show you what's happening in the memory. When the program starts execution, initially the main method is invoked. Some part of the memory from the stack is allocated for execution of a function. All the local variables and the state of execution of this function is saved in this particular section. We also call this stack frame of a function. Here in this main method, we have not declared any local variable. We just set head to null, which we have already done here. Now the next line is a call to function insert. So the machine will set the execution of this particular method main on hold and go on to execute this call to insert. So insert comes into this stack, and insert has a couple of local variables. It has two arguments, data and this variable n. This stack frame will be a little larger because we will have a couple of local variables. And now we create this another local variable, which is a pointer to node temp1, and we use the new operator to create a memory block in the heap. And this guy temp1 initially stores the address of this memory block. Let's say this memory block is at address 150, so this guy stores the address 150. When we request some memory to store something on the heap using new or malloc, we do not get a variable name, and the only way to access it is through a pointer variable. So this pointer variable is the remote control here, kind of. So here when we say temp1.data is equal to this much, through this pointer, which is our remote, we are going and writing this value 2 here, and then we are saying temp.next equal null. So null is nothing but address 0. So we are writing address 0 here. So we have created a node, and in our first call n is equal to 1, so we will come to this condition. Now we want to set temp1.next equal head. temp1.next is this section, this second field, and this is already equal to head. Head is null here, and this is already null. Null is nothing but 0. The only reason we set temp.next equal head will work for empty case is because head would be null. And now we are saying head is equal to temp1. So head guy now points to this because it stores address 150 like temp1. And in this first call to insert, after this we will return. So the execution of insert will finish. And now the control returns to the main method. We come to this line where we make another call to insert with different arguments. This time we pass number 3 to be inserted at position 2. Now once again, memory in the stack frame will be allocated for this particular call to insert. The stack frame allocation is corresponding to a particular call. So each time the function execution finishes, all the local variables are gone from the memory. Now once again in this call, we create a new node. We keep the address initially in this temporary variable temp1. Let's say we get this node at address 100 this time. Now n is not equal to 1. We will move on to create another temporary variable temp2. Now we are not creating a new node and storing the address in temp2 here. We are saying temp2 is initially equal to head. So we store the address 150. So initially we make this guy point to the head node. And now we want to run this loop and want to keep going to the next node until we reach n-1th node. In this case, n is equal to 2, so this loop will not execute this statement even once. N minus 1th node is the first node itself. Now we execute these two lines. The next of the newly created node will be set first, so we will build this link. Oops, no, temp2 dot the next is 0 only, so even after reset this will be 0. And now we are setting temp2 dot next as temp1, so we are building this link. And now this call to insert will finish, so we go back to the main method. So this is how things will happen for other calls also. So after everything we have inserted, when we will reach this print statement in the main function, our list will be something like this in the memory. This is a little messy. I've chosen this addresses as per my convenience for the sake of example. And now print will execute, and once again I'm using a temp variable in print. By now it should have been clear to you why we use temp variable again and again, and why this variable head that stores the address of the first node is so important. Now what if this head was not global? What if we would have declared this head inside the main method? We have talked about this in our previous lesson. Head will not be accessible everywhere, so in each call to these functions, in each call to insert, we will have to return some value from the function to update this head, or we will have to pass this head by reference. We have talked about this in our previous lesson. So this is it for this lesson. In our next lesson we will see program to delete a node at a particular position in the list. So thanks for watching. In our previous lesson, we wrote program to insert a node at nth position or a given position in a list, in a linked list. Now in this lesson, we will write a program to delete a node at any given position in a linked list. So once again, I have drawn a linked list here. We have 4 nodes in this list at addresses 100, 200, 150 and 250 respectively. So this is my example of a linked list of integers, and let's say we number the positions on a 1 based index. So this is the first node in the list, and this is the second node, this is the third node, and this is the fourth node. When we talk about deleting a node from the linked list, we will have to do 2 things. First, we will have to fix the links so that the node is no more a part of the list. Let's say in this case we want to delete the node at third position, so we will go to the second node. For nth node we will have to go to the n-1th node, and we will have to set the link part of the n-1th node as the link of the nth node, which will be the n+1th node. So we will cut this link, and now this node at address 150 is not part of the linked list, because when we will traverse the linked list, we will go from address 100 to 200, and from 200 we will go to 250. This is one scenario for deletion in which we have a node before and a node after. There will be special cases like we may want to delete the node at the first position or the head itself. In that case we will have to point head to the second node. We will have to build this link. We will talk about all these special cases in our implementation. Let's first understand the logic. Now, fixing the links is not good enough because all that we do when we fix the links is that we detach the node from the linked list so that it is no more accessible, but it is still occupying space in the memory. As we know, a node is allocated space from what we call the dynamic memory or the heap section of the memory. We have talked about this earlier. In C or C++, we have to explicitly free this memory when we are done using it because it is not automatically deallocated. And memory being a crucial resource, we do not want to consume it unnecessarily when we do not need it. So the second thing that we will have to do is we will have to free the space that's being taken by the node, and that's when the node will actually be deleted from the memory. So let us now write code for this. I'm writing my C program here. The first thing that I have done is I have defined a node which is a structure with 2 fields, one to store data and another to store address of the next node. So the second field is a pointer to node. Now to create a linked list, we will have to first create a pointer to node, a variable which is pointer to node, and that will store the address of the head node or the first node in the list. And now I want to define three functions. First, insert function that will take some value, some data to be inserted into the list and always insert this value at the end of the list. Then I want to define a print function that will print all the elements in the list. We have defined this variable head as a global variable, so it will be accessible to all these functions. And the third function that I want to write is delete, that will take the position n of the node to be deleted and delete the node at that particular position. We will go back to implementing these methods. First I'll write the main method. So in the main method, first what I'll do is I'll set head as null. So at this stage the list is empty, and then I'll make a couple of calls to insert function to insert some integers in the list. So after this fourth insert, the list will be 2, 4, 6, 5 because we are always inserting at the end of the list. This insert function will insert the node at the end of the list. Now what I want to do in my main method is I want to ask user for a position, and I'll input this position from the console, and then I'll delete the node at this particular position, and then I'll print the whole linked list. Let's also make a call to print after all the inserts. Okay, so this is what we want to do in our main method. We want to insert 4 integers in a linked list to create a list 2, 4, 6, 5 in this order. And then I want to print the list. Then I want to input a number from the console and delete the node at that particular position. Now let us assume that we will always give a valid position, and in my implementation also I will not handle the error condition when position will not be valid. We have seen implementation of insert and print earlier, so I will not go into their implementation details. What I'll do now is I'll implement delete function. Now in my delete function, let's first handle the case when there is a node before the node that we want to delete. So we have an n-1th node. What I'll do is I'll first create a temporary variable that is pointer to node and point this to head. And using this temporary variable, we will go to n-1th node. To go to the n-1th node, we will have to run a loop n-2 times, and we will have to do something like this. temp1 is equal to temp1 dot next. Now what I'll do is I'll create a variable to point to the nth node, name this temp2, and this will be equal to temp1 dot next. And now I can fix the link. I can say that adjust the link section, the link part of n-1th node to point to n+1th node, which will be temp2 dot next. Now our link is fixed, and this variable temp2 stores the nth node reference to the nth node. So we can make a call to free function. Free function deallocates whatever memory is allocated through malloc. If we were using C++ and if we would have used new operator, we should have said delete temp2. Okay, now we should be good. This much code will work for scenarios when we have an n-1th node, and even if there is no n+1th node, if n+1th position is null, this will work for that scenario. I'll leave that as an exercise for you to validate. We have not handled one special case when we want to delete the head node. So if n is equal to 1, then what we want to do is we just want to set head as temp1 dot next. Temp1 is right now equal to head, and now head has moved on to point to the second node, and temp1 still points to the first node. So links are fixed, and we can free the first node, which is now detached from the linked list because head is now pointing to the second node. Okay, so this is our delete function. I have missed one thing here. For n not equal to 1, we should not execute this section of the code. So either we put an else statement after this, or what we can do is we can say return after we execute these statements for this condition. Now this code should work if I've got everything right. So let us now run this and see what happens. I have already written the insert and print functions. I'll come back to this main function. This is my list 2, 4, 6, 5, and I can enter any of the positions 1, 2, 3 or 4. So let's first say we want to delete the head node, and we are printing the list after deleting a particular node. So the list now is 4, 6, 5. This seems to be correct. Let us run this again, and this time I delete number 5 from position 4. The list is now 2, 4, 6, which is correct again. Similarly, if I enter position 2, the list is 2, 6, 5, which is correct. So we seem to be good. I'll quickly walk you through this code in the logical view to make things further clear. Let's say we first make a call to delete node from the first position. That is, we want to delete the head node. So in this code, what we are doing is we are first creating a variable temp1, which is pointer to node. Initially, temp1 is equal to head, so it stores the address 100, so it points to the head node. Now n is equal to 1, so we come to this instruction. Head is equal to temp1 dot next. Actually, this is temp arrow dot next, but while reading we read this as temp1 dot next. This is nothing but a syntactical sugar for this statement, asterisk temp1 dot next. So we are dereferencing this pointer variable to go to this node and then accessing the next field of this node. Now we are saying head is equal to temp1 dot next. So head is now 200. So we are building this link and breaking this link. And now in the next line we say free temp1. So we want to free the memory which is being pointed to by this variable temp1. Temp1 still points to this node at address 100. So this node now will be cleared from the memory. And now we return, so this function does not execute any further. It finishes its execution. Once the function execution finishes, temp1, which was a local variable, also gets cleared from the memory. Head is a global variable, so it does not get cleared. This is how we know the linked list. This is the identity of the linked list, this particular variable head. Let's rerun this code again, and this time I want to delete the node at third position in the list. I have drawn this initial list. So once again we create this variable temp1. We say that the address here is equal to 100. So it points to the head node or the first node. And now n is not equal to 1, it is equal to 3. So we come to this particular loop. N is equal to 3, so this loop will execute exactly once. This statement will execute exactly once. So temp1 will now move to address 200. So temp1 is now pointing to the second node. This is what we wanted to do. We wanted temp1 to point to n-1th node. N is 3 here. Now we create another variable, another pointer to node, temp2. And we set this guy as temp1.next. temp1.next is 150, so we set this guy as 150. So this guy points to the nth node or the third node. Now in the next line we are saying that temp1.next, this value which is 150 right now, is now temp2.next, address of the n+1th node or fourth node. So this guy will now be 250. So we are building this link and we are breaking this link. So we have fixed the links, and now finally we are saying that free the memory which is being pointed to by temp2. So now this third node, the memory block, will be deleted from the memory. And once this function execution finishes, all the local variables temp1 and temp2 will be cleared, and this is what the list will be. This node at address 250 will now be the third node. So this was deleting a node at a particular position in the linked list. We can also have a problem where we may want to delete a node with a particular value. You can try implementing it. In the coming lessons, we will see more problems on linked list. So thanks for watching. In our lessons on linked list, so far we have implemented some of the basic scenarios like inserting a node in linked list and deleting a node from linked list. In this lesson we will write code to reverse a linked list. This is one of the most favorite interview questions, and this is a really interesting problem. So let me first define the problem. Let's say we have been given a linked list of integers like this. So this is our input. We have 4 nodes in this linked list, at addresses 100, 200, 150 and 250 respectively. I always write these addresses in the logical view because it's really important that we visualize how things are in the memory and what is what. Like this first node that we also call the head node is being pointed by this particular variable named head. So this variable is basically storing the address of the head node. This variable is only a pointer. This is not the head node itself, and we do not have any other identity of the linked list except the address of the head node. So given a linked list like this, if we have to reverse it, and by reversing we do not mean moving around data, like we cannot move 5 at address 100, 2 at address 250 and do something like this. We actually have to adjust the links. So our output should be something like this. The head pointer should point to this node at address 250, and we should go like 250 to 150, 150 to 200, and this node at address 100 should have address 0 or null. In each of these nodes, this first field in red is the data part and the second field is the address part. So this is what we will get when we will reverse the list. There are two approaches to solve this problem. One is an iterative approach where we will be using a loop. We will traverse through the list, and at each step we will revert one of the links. Another solution is using recursion. In this lesson we will try to understand the iterative solution. So coming back to our input list, the iterative solution is relatively easier to understand. What we can do is we can traverse the whole list, and as we go to each node we can adjust the link part of that node to make it point to the previous node instead of the next node. So we will start at the first node. At each step we want to reverse the link, so we want to make the node point to the previous node instead of the next node. For the first node there is no previous node, so let's say the previous node is null, and now we want to cut this particular link and we want to build this particular link. So we will simply change the address field to 0, and we have reversed the link part of this particular node. And now we will go to the next node in the list. We will come to this node. Of course the question would be, how would we go to the next node if we have broken this link here? We will come back to that in our implementation details. Let's say we are able to traverse the list and go to each of the nodes at each step. Let's say we store all the relevant information to do that in some temporary variables. Now at this node again we will reverse the link, so the address part will be set as 100 here. Now we will go to the next node at address 150. Once again, to reverse the link we will set the address as 200 here. So we will break this link, and basically we are building this link. And now we will go to address 250, the next node. We will set the address 150 here, so we will cut this link and build this link. And finally, when we have reached the last node, we will adjust the address in this head variable to 250. So this particular variable, this particular pointer will point to this node at address 250, and our linked list is reversed now. So let us implement this particular logic in a real C program. I will redraw the original input list. In my C code I will define node as a structure like this. This is how we have defined a node in all our previous lessons. So there will be two fields, one to store the data which will be of type integer, and another to store the address of the next node. We will name this field next, and it will be of type pointer to node. And let's say head is a global variable, so head is a pointer to node. Head is a variable which is a pointer to node, and it is a global variable, so it is accessible to all the functions. We do not need to pass it around to functions. Now all I want to do in my code is I want to write a reverse function that will reverse the linked list which is pointed to by this particular pointer head. As we said, we will traverse the whole list, and at each step we will modify the link field of the node to make it point to the previous node instead of the next node. So how do we traverse a list? We would traverse a list in our C code something like this. We will first take a variable which will be pointer to node. Let's say we will name it temp, Then first we will set temp to head. By saying this, we will make temp point to the first node, and then we will run a loop like this. We will say that while temp is not equal to null, take temp to the next address with a statement like temp is equal to temp.next. In our problem here, we don't just have to traverse the list. As we traverse the list, we have to reverse the link. So we have to set the address field of a particular node as the address of the previous node instead of the next node. Now in a linked list, we would always know the address of the next node, but we would never know the address of the previous node. So as we traverse the list, we will have to keep track of the previous node in another variable. So what I will do here is something like this. I will also declare a variable named previous and initially set it to null, because for the first node or the head node, the previous node is null. And now in my loop, we will have to update both these variables, the variable temp that will store the current node and the variable prev that will store the address of the previous node. And now in my loop I can do something like this. At each step, if temp is our current node as we are traversing the list, then we will say that temp.next is equal to previous. So we will set the link part of the current node as the address of the previous node. In our example here, at the first step, we will say that temp.next will be 0. Null is nothing but address 0. So we will cut this link and we will build this link. Now we should be able to move temp to 200 now, and we should be able to move previous to 100 now in the next step. But there is a problem. As soon as we adjusted the link of this particular node at address 100 to make it point to null, we lost the address of the next node. So how do we move temp to this particular node at address 200? We cannot say temp equal temp.next now. If we say temp equal temp.next, now we will go to null. So this is a problem. So at each step in our iteration, before we set the link field of the current node to make it point to the previous node, we should store the address of the next node in a temporary variable, in another temporary variable. So what I'll do here is something like this. First of all, I want to name this particular variable temp as current, to mean that this is the current node at any stage in my iteration. So we initially set current to head, and then we are running the loop as while current is not equal to null. And then I have also declared one more temporary pointer variable named next. What I'll do at each step in my iteration inside the while loop is that first I'll say something like next is equal to current dot next. So first I'll store the address of the next node in this particular variable next. So in our example here, for the first node, initially things will look something like this. Now we can set the link part of the current node as address of the previous node with a statement like this. So when we will write the address 0 here initially, we will break this link and create this link. We will not lose the information about the next node. Now we can redefine our previous and current. So we will first move previous to current, and then we will move current to next. Please note that this particular variable next is a local variable in the reverse function, and when we say something like current.next, we mean the link field in the node, while when we simply say next, we mean this particular local pointer variable. So they're different. This is not current.next, actually this is current arrow next, which is an alternate syntax for asterisk current.next. So we use the asterisk operator to dereference that address, and then we access the next field. For the sake of saying, we say current.next or temp.next. So with these two lines in our loop, we are resetting our previous and current pointers. This is how we are traversing the list. If you see in the next iteration, current is 200, it is not equal to null. Null is 0. So we will go to this particular statement, next is equal to current.next. So next will now store the address 150, and now we will say current.next is equal to previous. So we will cut this link. Previous is 100 right now, so we will set 100 here. So basically we will build this particular link, and then we will first move previous to current and then move current to next. and we will go on like this. So finally we will reach a stage like this. When current will be equal to null, we will come out of the loop, and when we will come out of the loop, this particular variable previous, this particular pointer previous, will store the address of the last node. And there is one more thing remaining here. We need to adjust this particular variable head. This link at this stage does not exist, and in my code I'll say head should now be equal to the address in variable previous. So head is now 250. This is our new head, and now our list is reversed. There are a couple of things that I want to point out here. One thing is that we must see whether our implementation is working for all test cases, so we must also verify it for special or corner test cases. In this case, corner test case will be when the list is empty. In that case, head will be null, or when the list is having only one node. If you see, this particular implementation will work for these two scenarios. Give it some time and you should be able to figure it out. Let's now run this code with complete implementation of all the functions to insert and print nodes. In my code here, I have written reverse function to accept the address of the head node as argument, and then return the address of the head node after modification of the list, after reversal of the list. And then I have written the main method in which I'm declaring head as a local variable, and then I'm using a couple of insert functions. I'm making a couple of calls to insert function. Insert function also takes two arguments, the address of the head node and the data to be inserted, and it returns back the address of the head node. It could either be modified or not modified. Let's say we are inserting at the end of the list, so initially our list will be 2468, and then we are making a call to the print function, which I have written to print the elements in the list, and then I'm making a call to reverse and finally printing again. My logic of the reverse function remains the same, except that I've changed the method signature, and in the end I'm returning head, which will return the address of the head node. Let's say we have written all the other functions, insert and print, correctly. These are the two functions, insert and print. So let's now run this code and see what happens. Before the list is reversed, the output is 2468, and after the list is reversed, the output is 8642. Let us try this for the case when we have only one element in the list. So I'll comment out these three insert statements, and this also seems to be working. So this was reversal of linked list through iteration. In the next lesson we will write code to reverse linked list using recursion. So thanks for watching. In our series on linked list, so far we have implemented some of the basic operations like insertion, deletion and traversal. Now in this lesson we will write code to traverse and print the elements of a linked list using recursion. Prerequisite for this lesson is that you should understand recursion as a programming concept. Recursive traversal of linked list actually helps us solve a couple of interesting problems, but in this lesson we will keep it simple. We will just traverse and print all the elements in linked list using recursion, and we will write one simple variation to print all the elements in reversed order using recursion. We will actually not reverse the list, we will just print the elements in reversed order. So once again I have taken example of a linked list of integers here. We have 4 nodes. Each rectangle here is a node. It has 2 fields, one to store the data and another to store the address of the next node. Let's say we have 4 nodes at addresses 100, 200, 150 and 250 respectively. And of course we will also have a variable that will store the address of the head node. Let's name this variable head. Programmatically in our C or C++ program, a node will be defined something like this. We will have a structure with 2 fields, one to store the data and another to store the address of the next node. What we want to do in this particular lesson is that we want to write 2 functions. First we want to write a function named print that will take
address of a node as argument, we will pass this function the address of the head node. So let's name this argument head, and in this function we will use recursion to print the elements in the list. So for this particular example here, if we want to print a space separated list of all the elements, our output will be something like this. And we also want to write another function named reverse print. Here also we will take the address of a node, so we will pass this guy the address of the head node, and in this function we will use recursion to print the elements in the list in reversed order. So if we have to print a space separated list for this example, our output will be something like this. So let's first implement the print function. In my C code here, I'll declare print function like this. It will take as argument the address of a node, so that